Here's a system of differential equations written in matrix form. We have this eigenvalue equation, which is to subtract lambda off the diagonal and take the determinant. That gives you lambda squared plus 1, whose solution is plus or minus I. Now, when you have complex eigenvalues like this, you only need to find the eigenvector corresponding to one of the eigenvalues. So we choose lambda equals to I and see what we get for the eigenvector. So this is the eigenvector equation. We subtracted lambda off the diagonal as before, times the eigenvector has to equal to 0, 0. And if you do a cross down to see what the first equation is, this is the equation you get. You don't do the second line unless it's the first one gives you a 0, 0 in some rare cases. The second one is always equivalent to the first one. So we just write this down. And then the easiest way to find the solution of this system, this equation, is to take the coefficient of A and let it equal to B, and coefficient of B as the value of A without this minus sign. Or sometimes if this is plus, you have to make it negative, okay? And doing that gives you A equals to 2 and B equals to negative 3 minus I, and therefore 2 and negative 3 minus I is the eigenvector for eigenvalue I. Then the next process is to take the standard procedure of taking the eigenvector e to the lambda is I, lambda t, and this is one solution to this differential equation. Now, normally what you would do is to find the other eigenvector and write it as eigenvector times e to the lambda t for that one as well, and put c1 here and then plus c2 there. But the problem with that is it won't be real valued solutions. Because all these coefficients are real, when you solve such a differential equation, you're looking for real valued solutions. But writing it like that, you have all these i's, the imaginary number I here and there, and you get complex valued functions. So instead of doing that, we will just work with this single thing. Now the idea is, if this is a solution to the differential equation, its real part and the imaginary part will be separately real valued functions that satisfy the differential equation. And once you know that, then you hope that the two functions that you get will be linearly independent, which it always will be. And using those, you can write down the general solution for this system of ODE. Okay, so let's proceed. We're trying to find the real and imaginary part of this function. So we split 2, negative 3 minus I as these two. As you can see, this is the real part and this is the imaginary part. And then e to the it is equal to cosine t plus I sine t. This is called the Euler's identity. You FOIL first, outer, inner, less. So this is what you get. And then we have to work a little bit here. I times negative I, that's negative I squared. I squared is negative 1, so it would be positive 1 because it's negative of negative 1. This I here, you want to pull it outside. And if you do that, then it's clear that the first and the last are real valued functions already, but the middle two will always have I multiplied, so these will be the imaginary part. If we gather the first and the last, and also the middle two separately, and write it like this, you see that this is the real part, and this is the imaginary part, and so you hope that these are separate. I mean, you know that these two are separately the solution of this system of ODE, but you also hope that they are linearly independent. Okay, we're going to put these into a single column vector by doing 2 times cosine t plus 0 times sine t, that's what I wrote here. Negative 3 times cosine t plus 1 times sine t, that's what I wrote here. Do the same thing as well here. And if you check with Wronskians, if you put these two side by side and take that square matrix's determinant, you'll see that the Wronskian will be non-zero, which means these are linearly independent solutions of the given differential equation, the system of equations, and therefore you can write down the general solution of this system by taking C1 of this part and C2 of that part, and therefore that's the final answer.